Okay, before we dive into this week's exciting topics, I wanted to briefly recap what we covered last week, which was working through the introductory Kaggle courses on machine learning and pandas. I hope everyone had a chance to complete them and, more importantly, and some fun applying what they learned. If you run into any roadblocks or have any questions about the Kaggle courses, please don't hesitate to ask at our Discord channel. We are here to support each other. Last week, we started our machine learning journey by diving into the introduction to machine learning course on Kaggle. This course provided a great overview of the fundamental concepts from what machine learning is to how to train and evaluate basic models. We learned about main concepts. And of course, those hands-on exercises really helped solidify those concepts and gave us a first taste of working with real data. Because now I get different questions and I didn't see your certificates, so later we'll dive deeper in these concepts. It's crucial to get this knowledge. And of course, equally important was our work with the Pandas Kaggle course. Pandas is absolutely essential for any machine learning practitioner, and this course gave us a fantastic introduction to its capabilities. We learned how to use data frames, which are like tables or data, and series, which are like single columns from a table. And we also covered how to perform essential data manipulation tasks like cleaning and transforming data and how to do some initial analysis. The practical exercises on Kaggle were key to becoming familiar with Pandas library, but of course we'll dive into this later. So the most important takeaway from last week is that Kaggle is an invaluable resource for learning machine learning. It's a bad idea to skip these courses. As a combination of concepts, explanations, and practical expertise makes it a great way to build your skills. By completing the Intro to Machine Learning and Pandas courses, you now got a solid foundation to build upon. Your experience me working with real data in a structured environment, which is crucial for moving forward. But now we start and make step back in these courses and main concepts for those who skipped homework. In our Pandas journey on Kaggle, we started with the absolute essential, creating, reading, and rating data. This is the foundation upon which everything else in Pandas is built. Without these skills, we can't effectively work with any real-world data. Mastering these basic operations, creating, reading, and writing, is absolutely essential. It's foundation for everything else you do in Pandas. Without it, you can't even begin to explore, clean, or prepare your data for machine learning. The heart of Pandas is the data frame. Think of it as a table, rows and columns, just like a spreadsheet or SQL table. Data frames are incredibly versatile and are the primary way we organize and manipulate data in Pandas. We learned how to create a data frame from scratch, which is useful for small data sets or when we want to test something quickly. We also saw how to access and manipulate individual columns and rows with a data frame. Alongside data frames, we have series. A series is like a single column from a data frame. It's a one-dimensional labeled array capable of holding data of any time, integer, string, float, Python objects, etc. Understanding series is crucial because of many pandas operations work on a series basis. For example, you might perform calculation on a single column, a series within your data frame. While creating data frame and series manually is helpful for learning, the real power of pandas comes from its ability to read data from various sources. And the most common source you encounter is CSV files. We learned how to use them. Panda read CSV function to import data from CSV file directly into Panda's data frame. And exactly this is crucial skill because almost all real-world data sets you'll work with will be in some kind of file format, and CSV is one of the most popular. We discuss how to specify file paths, handle different delimiters, and even how to deal with missing data during the import process. Just as important as reading data is the ability to write data back out. We briefly touched on how to save your data frames back to CSV file using the to CSV function. This is essential for saving your work, sharing data, or even preparing your data for other parts of your machine learning pipeline. Once we've loaded our data into Pandas, the next crucial step is being able to access and manipulate specific parts of it. That's what the lesson indexing, selecting, and assigning is all about. It's like having a map to your data and knowing how to pinpoint exactly what you need. Pandas provides powerful ways to select data using labels, the names of your rows and columns. The lock indexer is our primary tool for this. It allows us to select rows and columns based on their labels. For example, we can use look to get all the data for a specific customer or extract a particular column like product price. This is incredibly useful when you worked with data where the labels have meaning. For instance, if the row labels are dates or customer IDs. So sometimes we don't know the labels, or we just want to select data based on its position in the data frames. That's where iLog comes in. Instead of labels, iLog uses integer positions to select rows and columns. So uh, data where the order is important, or when you need to select data based on its numerical index. Mastering indexing, selecting, and assigning is fundamental to work effectively with pandas. It's how we navigate our data, extract the information we need, and prepare it for analysis and modeling. In the next sessions, we'll build, of course, these skills and explore even more powerful data manipulation techniques. And now that we know how to access and select data, the next step is often to summarize it and extract meaningful insights. As the lesson summary function and maps equips us with the tools to do just that. It's about getting a high-level view of our data and efficiently transforming it when needed. Pandas provides a rich set of summary functions that allows us to quickly calculate a key statistic about our data. Functions like mean give us the average value of column. Count tell us how many non-missing values there are. Min and max reveal the extremes. These functions are, of course, incredibly useful for getting a sense of the distribution of our data and identifying potential patterns or outliers. For quickly and comprehensive statistics overview, the describe function is invaluable. It provides a summary of descriptive statistics for all numerical columns in our data frame, including count, mean, standard deviation, min, max, and quantities. This is a fantastic way to get a quick snapshot of the distribution and central tendency of your numerical data. Sometimes we need to transform our data at the element level to apply a function to each individual value in a series. The map function is perfect for this. It allows us to apply a custom function or a predefined function to every element in a series. For example, we might want to convert all products names to lowercase or apply a discount percentage to each price. For more complex transformations that involve multiple columns or require more control, we can use the apply function. Apply function can be used to apply function to an entire row or column. This is particularly useful when we want to create new features based on calculations involving multiple exciting features, or when we need to perform more sophisticated data cleaning or transformation steps. Summary functions and maps are essential tools for data exploration and preprocessing. They allow us to quickly understand our data, identify patterns, and of course transform it efficiently. And often we want to analyze our data in the context or different categories. For example, we might want to know the total sales for each product, the average customer spending by region, or the number of orders placed each year. This lesson, grouping and sorting, provides the tools to structure and organize our data to answer these kinds of questions. The group by function, for example, is incredibly powerful analyzing data based on categories. It allows us to group our data frame by one or more columns. For example, we can group our data by product name to analyze sales performance for each individual product, or by year to understand trends over time. Once we've grouped our data, we can then apply aggregation functions to extract meaningful insights. After grouping our data, we typically want to calculate some summary statistics for each group. This is where aggregation functions like sum, count, mean, median, max, mean come in. For instance, if we grouped our data by product name, we could use sum function to calculate the total sales for each product, count function to count the number of orders for each product, or mean function to find the average price. These aggregations provide valuable insights into the performance and characteristics of different groups. Once we've calculated our summaries, it's often helpful to sort the results to make them easier to interpret. The sort value function allows us to sort our data frame based on one or more columns. For example, we might want to sort our product sales from highest to lowest, or sort customers by their spending. Sorting makes it easier to identify trends, outliers, or top performance. The real power comes from combining group function and sort values function. We can group our data by a category, apply an aggregation function, and then sort the result to get a clear picture of the performance of different groups. For example, we could group our data by region, calculate the total sales for each region, and then sort the regions from highest to lowest sales. Exactly this gives us a powerful way to analyze and understand our data. Grouping and sorting are fundamental techniques for data analysis and reporting. They allow us to structure our data, extract meaningful insights, and present our findings clearly. These skills are essential for understanding patterns and trends in our data and for communication those insights to others. In the next lessons, of course, we explore even more advanced techniques for data manipulation and analysis. But before we can effectively analyze or model our data, we need to ensure its quality. This lesson, Data Types and Missing Values, focuses on two critical aspects of data quality: understanding the data types of our columns and handling missing values. These are essential steps in preparing our data for analysis and machine learning. Every column in a pandas data frames has a specific data type: integer, float, string, boolean, date, time, etc. Understanding these data types is crucial because it affects how we can manipulate and analyze the data. We learn how to use the dtype attribute to check the data type of a column. We also saw how to convert data types using the type function. For example, we might need to convert a string column representing dates into a date-time type so we can perform time-based analysis or convert a column of floats to integers if the decimal precision is unnecessary and is taken up memory. Real-world data is rarely perfect and often contains missing values. These missing values can arise due to various reasons: incomplete records, data entry errors, or sensor malfunctions. It's crucial to identify these missing values because they can significantly affect our analysis and model performance. We learned how to use the is-null function to create a Boolean mask that indicates which values are missing, true, and which are present, false. This allows us to see where the gaps in our data are. Once we've identified missing values, we need to decide how to handle them. Pandas provides two main approaches: filling them in, imputation, or dropping the rows or columns containing them. We explored the fill now function, which allows us to fill missing values with a specific value, like the mean, median, or constant, or using more sophisticated methods like forward fill or backward fill. We also learned about drop now function, which allows us to remove rows or columns that contain missing values. The choice between filling and dropping depends on the amount of missing data, the nature of your data, and the specific analysis you are performing. It's important to think carefully about how we handle missing data. Simplify filling all missing values with the mean. For example, might not be the best approach if the data is not missing at random. Sometimes missingness itself can be informative. There are more advanced imputation techniques, but we'll cover those later. For now, it's important to be aware of the potential impact of missing data and to choose an appropriate strategy. Understanding data types and handling missing values are essential steps in the data cleaning and preprocessing pipeline. Ensuring data quality is crucial for obtaining reliable insights and building robust machine learning models. Often, the data we need for analysis is spread across multiple files or comes from different sources. This final lesson in our Pandas series, renaming and combining, covers the essential techniques for bringing this data together and ensuring it's organized and consistent. Sometimes columns, names aren't very descriptive or consistent with our naming convention, so the rename function allows us to easily change column names to make our data cleaner and easier to work with. This is important for code readability and for ensuring consistency when combining data from different sources. When we have data that's structured similarly but comes in multiple pieces, for example, data from different years or different regions, we can use the concat function to step it together. Concat function allows us to combine data frames vertically, adding rows, or horizontally, adding columns. This is useful for aggregating data from multiple files or combining data from different parts of a larger data set. The join function is another way to combine data and is particularly useful when we want to align datasets based on the indexes labels. It's similar to merge function, but it uses the index as the key for combining data. This can be more efficient in certain situations, especially when we're working with time series data or data where the index has a special meaning. In this Pandas course, we've covered a wide range of essential skills for data manipulation and analysis. We've learned how to create, read, and write data, select and modify specific elements, summarize and transform data, group and sort data, handle missing values and data types, and, as we've just seen, rename and combine datasets. Mastering these skills empowers you to efficiently analyze and manipulate data in Python, which is a crucial foundation for any machine learning project. Now that you have a solid understanding of pandas, we're ready to move on to the next stage, applying these data manipulation skills in the context of feature engineering. In addition to our pandas work, another part of your homework was to begin the Introduction to Machine Learning course in Kaggle. This course provides a great overview of the fundamental concepts, and we'll be discussing the first lesson, how models works, which introduces the idea of machine learning models and focuses on a simple but important model called decision tree. Decision tree are like flowcharts. They make decisions by asking a series of questions about the data. Each question corresponds to a feature of the data, and the tree balances based on the answers to those questions. Eventually, the tree leads to a prediction. The key is how the decision tree learns which questions to ask and where to branch. The model learns these rules from the training data. It looks for the features that are most predictive of the target variable. Now, this thing we are trying to predict, like house price in our example. It tries to find the questions that best split the data into groups that are as similar as possible with respect to the target variable. This process is repeated recursively, creating the branches of the tree. While decision trees are relatively simple, they're also incredibly important because they serve as a foundation for more advanced models. Many other powerful machine learning algorithms like random forest, gradient boosting, are actually built upon the principles of exactly decision trees. So, understanding how decision trees works is a crucial first step in your machine learning journey. This lesson provides a great introduction to the core idea of machine learning models, learning patterns from data to make predictions. Understanding how decision trees work give us a concrete example of how this learning process happens. Continuing our journey throughout the Intro to Machine Learning Kaggle course, we are now focusing on a crucial step before we even start building models, basic data exploration. This lesson emphasizes why it's so important to understand our data before we jump into modeling. The first thing we need to do is load our data into a format we can work with. Just like we learned in the Pandas course, we use the Pandas library in Python to load datasets. Specifically, we'll often use Panda read CSV function to load data from CSV files, which are a common format for machine learning datasets. This step brings our data into Pandas data frame, making it easy to inspect and, of course, analyze. Once our data is in a data frame, we want to get a sense of its overall characteristics. We use Pandas function like describe to generate descriptive statistics. This gives us information like the mean, median, standard, deviation, minimum, maximum values for each numerical column. These statistics give us a quick overview of the distribution and, of course, range of our data, helping us to identify potential outliers or unusual patterns. Basic data exploration is absolutely essential before building any machine learning model. Understanding our data helps us identify potential problems, choose appropriate models, and even make informed decisions about data preprocessing. A crucial part of data exploration is checking for missing values. Real-world data sets often have missing data, and these gaps can affect the performance of our machine learning models. We can learn how to use functions like isNull to identify missing values in our data frame. This allows us to see which columns have missing data and how much missing data there is. Why is checking for missing values so important? Because many machine learning algorithms can't handle missing data directly. We'll need to detect how to deal with these missing values, whether we fill them in imputation or remove the rows or columns that contain them. Understanding the extent and patterns of missing data is crucial for making informed decisions about how to handle them. Basic data exploration is absolutely essential before building any machine learning model. Understanding our data helps us identify potential problems, choose appropriate models, and make informed decisions about data properties. This lesson, your first machine learning model, walks us throughout the process of defining the problem, selecting the data, training a model, and making predictions. We will use the decision tree model, which we already learned how it works. Every machine learning task starts with defining what we want to predict. This is called the target variable. It's the output we want our model to generate. For example, if we are predict house price, the target variable is price. If we are classifying images, the target variable is the category of the image. Identifying the correct target variable is crucial because it determines what our model is trying to learn. Next, we need to select the features. These are the input variables that our model will use to make predictions. They are the information we give to the model to learn from. In our house price example, features might include the size of the house, the number of bedrooms, the location, etc. Choosing the right features is essential for building a good model. We want to select features that are relevant to target variables and that provide enough information for the model to learn effectively. In this lesson, we focus on training a decision tree model. We use this Scikit Learn library in Python, a powerful tool for machine learning to train our first model. We feed our selected features and the target variable to the model, and the model learns the relationship between them. This is the training process. The model learns the patterns in the data so it can make predictions on new data. Once our model is trained, we can use it to make predictions on new unseen data. This lesson provides a complete workflow of building a basic machine learning model from defining the target and selecting features to training the model and making predictions. Now that we know how to build a public machine learning model, we need crucial question. How do we know if our model is any good? This lesson, model validation, addresses this very important question. It's not enough to just train a model. We need to evaluate its performance reliably. A common mistake that beginners make is evaluating their model's performance only on the data it was trained on. This call lead to overly optimistic and misleading results. Why? Because the model has already seen the data. It's like, for example, giving a student the answer key before the test. They'll do great on the test, but that doesn't mean they've already learned the material. Our model might perform perfectly on the training data, but fail miserably on new, unseen data. The solution to this problem is to split our data into two separate sets, a training set and testing set. We train our model on the training set and then we evaluate its performance on the testing set. The testing set is data that the model has never seen before. This gives us much more realistic estimate on how well our model will perform on new real-world data. By evaluating our model on the testing set, we can measure its accuracy on unseen data. This gives us much more reliable measures of how well our model is doing. We can use various metrics, which we'll discuss in more detail later, to quantify the model's performance on the testing set. This helps us to compare different models and choose the best one for our task. Model validation is absolutely essential in machine learning. Without proper validation, we can just trust our model's predictions. The train-test split is a fundamental technique for ensuring that our models are robust and generalize well to new data. It prevents us from being fooled by overly optimistic results on the training data. We learned how to train and validate models, but how do we know if our model is just right? In this lesson, underfitting and overfitting explores two common problems that can arise when training machine learning models underfitting or overfitting. Finding the sweet spot between these two extremes is crucial for building effective models. A simple model may not capture important details under fitting, while a complex model may memorize the training data and fail on new data, overfitting. So the goal was to find the right balance so our model generalizes well to new data. When building models, we face a trade-off. A simple model might underfit. It fails to capture important patterns and performs poorly even on the training data. Think of it like trying to predict house price using only the size of the house, ignoring location or number of bedrooms. On the other hand, a complex model might overfit. It memorizes the training data, including noise, and performs great on training data but poorly on new data. It's like memorizing practice questions but failing the real test. Our goal is to find the sweet spot, a model that's complex enough to learn the real patterns, but not so complex that it memorizes noise. Our goal is to find the right balance between this underfitting and overfitting. We want a model that is complex enough to capture the important patterns in the data, but not so complex that it memorizes the noise. This balance is what we call generalization, the ability of the model to perform well on new, unseen data. A model that generalizes well is one that performs well on both the training and testing sets, although usually slightly better of the training set. The key is to find exactly the sweet spot. One way to control this complexity is by adjusting the tree's depth using max leaf nodes. A shallow tree has few splits, which can lead to underfitting. A deep tree with many splits can lead to overfitting. The max leaf nodes parameter limits the number of leaves or final decision points in the tree. Fewer leaves mean a simpler tree, while more leaves mean a more complex tree. We want to find the optimal number of leaves that balances underfitting and overfitting, leading to the best performance on unseen data. We use validation data to find this sweet spot. We train on the training data and then we evaluate performance on the validation data. By experimenting with different values for max leaf nodes and measuring the mean absolute error on the validation set, we can identify the number of leaves that gives us the best performance on unseen data. This helps us choose a model that generalizes well and avoids the pitfalls of underfitting and overfitting. The goal is to minimize the validation error, indicating the best balance between model complexity and generalization. Understanding underfitting and overfitting is crucial for building effective machine learning models. It's a balancing act. We want a model that learns the important patterns without memorizing the noise. In the next lessons, of course, we'll explore techniques for diagnostic underfitting and overfitting and strategies for finding that optimal balance. We've seen the trade-off with decision tree. Deep trees overfit, shallow trees underfit. This lesson, random forests, introduce a powerful technique to address this, leading to much better prediction. A random forest uses many decision trees. Instead of one tree, it averages the prediction of each tree in the forest. The ensemble approach generally leads to much better accuracy than a single tree. So, You go the foundation knowledge and some hands-on experience thanks to Kaggle. This week we're taking it to the next level. We're diving deeper into intermediate machine learning, focusing on feature engineering. Feature engineering is a crucial step in creating truly powerful and effective machine learning models. It's all about transforming the data you've learned to manipulate with pandas into even more meaningful inputs that can dramatically improve our model's performance. It's often said that feature engineering is more art than science, and it's where you can really make a big impact on your model's accuracy. So everyone who did homework and finished necessary courses get 2 certificates, which you can receive at Kaggle Learn tab. Okay, let's start with our topic for next week, intermediate machine learning and feature engineering. Intermediate machine learning is the next step after learning the basics. It helps improve model accuracy and efficiency by handling missing data, automating workflows, and using advanced validation methods. These techniques help us move from beginner machine learning models to real-world applications. Why is intermediate machine learning what it is and why it's so important? Intermediate machine learning builds upon the basics and help you develop the skills needed to handle real-world data set more effectively. This level of machine learning focuses on improving model quality, handling common data uses, issues, and optimizing performance. And what is feature engineering? Feature engineering is the process of transforming raw data into useful inputs for machine learning models. Well-engineered features can significantly boost model accuracy and effectiveness. So, intermediate machine learning course. This course helps improve your machine learning models with practical techniques. Learn to handle missing values and categorical data effectively. Use pipelines for cleaner, more efficient model building. Master cross-validation for better model validation. Explore XGBoost, a powerful modeling technique for structured data. Avoid data leakage, a common mistake that can ruin model performance. Each topic includes hands-on exercises using real-world housing price data. Completing these lessons will help you build stronger, more reliable machine learning models. Feature engineering. This course focuses on feature engineering, a crucial step in improving machine learning models. You learn to select, transform, and create features to boost predictive power. Topics include mutual information, target encoding, clustering, and PCA. Hands-on exercises use Kaggle house price dataset for practical learning. Mastering feature engineering helps build better, more interpretable models. And Code Lab from Google, Cloud Feature Engineering is, of course, our optional homework. So that brings us to the end of today's session. Thank you all for your participation. Remember to complete your homework on Kaggle, both the intermediate machine learning feature engineering course. If you have any question, feel free to reach out in our community Discord channel. This session was recorded and will be available on our GDG Ahlen YouTube channel later. You can rewatch it at your convenience. Please don't forget to submit the post-event feedback form. Your insights help us improve and make future sessions even better. Once again, thank you for joining. We look forward to seeing you in our next session next Sunday. Until then, keep learning, experimenting, and building with AI. See you on our next session. See you next